Allow me to begin my presentation. Hello, my name is Gregory Pell. I'm PhD student in Seoul National University. My supervisor is Professor Myung-Shin Im. Now I'm going to introduce our GECKO project aiming to find the optical counterpart of gravitational wave. And I will briefly discuss about the synergies between our facilities with Gemini. The gravitational wave, the GW, is a repulse of space-time caused by extreme acceleration of the object. One of the main GW source is compact binary collisions. For example, there are binary neutron star merger and black hole neutron star merger and black hole merger. If this system contains more than one neutron star, then we can expect the kilonova explosion powered by radioactive decay of heavy elements. So we can expect not only gravitational wave signal, but also the electromagnetic wave counterparts from binary neutron star merger. GW17817 is the best and the only example. 2017, August 17, the LIGO and Virgo gravitational wave detectors observed the gravitational wave signal by binary neutron star merger. And subsequently, the satellite also detected the short gamma ray burst, and the astronomers all around the world started to find the its EM counterpart. So 11 hours after, they found it in the massive galaxy NGC 4993. After that, various observations, for example, radio observation and polarimetry and spectroscopy are conducted. Then this historical event opened a new way of exploring the universe, namely the GW multi-messenger astronomy. GW EM counterpart makes us better understand the GW source. The EM counterpart pinpoints the exact position of the GW source, so we can confirm the link between binary neutron star merger, short gamma ray burst, kilonova, and gravitational wave. We can also constrain the lateral kilonova models by comparing with the observational data. We also identify the GW host galaxy, so it means we can study the environment of binary neutron star merger. And I want to address the third one, the GW standard siren. We can measure the Hubble constant by combining GW distance and with the redshift of host galaxy. But here are some problems that there is only one GW EM counterpart, so it is hard to do statistical approach yet. And next one is there is some degeneracy between GW distance and its inclination. But fortunately, the observational data of kilonova and short gamma ray burst can constrain its inclination. The last one is the fastest early detection is still 11 hours after the GW event. According to the theoretical studies about this, the emission, early emission, the early emission has crucial information about its nature, for example, explosion mechanism and the origin of heavy elements. So rapid identification of EM counterpart is the keys to the success of multi-messenger astronomy. But nothing goes easy, and there are two main obstacles for rapid follow observation. The first one is kilonova is really relatively faint event and it decays very fast. As you can see on the left figure, kilonova has dimmer, fainter brightness than supernova, about few magnitudes, and it decays within a few days. The next one is the localization area is really poorly constrained. The GW17817 is kind of a very lucky event because it was close to us and its localization area is just a 30 square degree. But as you can see, other events have the hundreds to thousands scale degree. So it's hard to cover whole area within a few days. So to overcome those obstacles, we need the optimal facilities and observing strategies. So now I'm gonna introduce the GECKO project. The network of telescope consists of 1 meter class telescope. And thanks to globally distributed facilities, we can follow up the gravitational wave event anytime and anywhere. And not only that, we have two secret reference. The first one is KMT-net of CASI, and second one is 7-dimensional telescope. The KMT-net is 1.6 meter telescopes and located in 3 sites, South Africa, Chile, and Australia. So there is an advantage to do continuous observation. And the 7DT is also wide field of instrument. 7DT is the biggest scale of multiple telescope system with 20 telescopes. What makes 7DT special is 7DT has the medium band filter system for low resolution spectroscopy. So 7DT is specialized to identify the kilonova. So why the project name is GECKO? My supervisor, Myung-shin, usually explains like this. This is because the GECKO sticky hands never miss their EN counterpart. And it is also a good explanation, but I think, as you know, GECKO has very special eye because GECKO's eye has a wide field of view and GECKO has no eyelids, so they never close eyes before they find the EN counterpart. So GECKO name is really interesting and cute. So please remember our project. Okay. So there are two strategies to find GW counterpart. The first one is galaxy targeted observation. First, we prioritize the GW host galaxy candidates. Then we observe them one by one in order with using the rare field of view instruments. And next one is tiling observation. Tiling observation just covers the localization area with the wide field of view telescope, for example, 7DT and KMT-net. I want to talk about galaxy targeted observation more. So if we get a GW alert, then we know the projector distance range, the localization area. So within this volume, we select the host galaxy candidates from the galaxy catalog. We use the GREAT catalog, contains the information about the 3 million extended source. After selection, the prioritization is really important. So we use 3 factors. The first one is the position of the host galaxy candidates on the localization area. The next one is distance difference between gravitational wave, the gravitational wave, and the host galaxy candidates. The last one is the most important thing. We use the K-band luminosity as a proxy of stellar mass of galaxy. So according to the simulation result, it says stellar mass of host galaxy has tighter correlation with the binary transfer merger rate than star formation rate. So the brighter K-band luminosity means the more massive host galaxy, and that means the higher binary transfer merger rate. So using these 3 factors, we prioritize, we score each host galaxy candidates, then we observe them one by one in order. Next, we have to check whether this methodology is good or not in real world. So we applied it to GW17A17 case. So as you can see, there are 40 host galaxy candidates within the localization area and distance range. And we score each candidate. Then as you can see, NGC 4993 has the highest score, the answer of the galaxy. The next, if we observe the 14 highest scored host galaxy candidates, then we can get more than 90% of cumulative score. It means we can do efficient efficient follow observation. So we can learn that a prioritization method works well for at least this event. And we follow up lots of GW events in observing launch 3. And here is one of the results about the GW190425, the second binary transfer merger. As you can see, this event was really poorly constrained. It has, because of the duty cycle of gravitational wave detectors, its localization area is about 7,000 square degree. So, but there is a chance to have the EN counterpart. We follow up this event. We started the follow observation 9 minutes after the GW alert. And we covered about 40 square degree, and we covered 600 numbers of galaxies. It's compared to the 10% of the total number of galaxies. But in the view of score, we covered about 27%. So it means we marginally conducted the efficient follow observation. As a result, we found 10 transient candidates, but most of them are supernovae, and including us, nobody found the GW counterpart. It makes us very sad, but we can constrain the expected kilonova properties with the upper limit, the depths, and we can check our facility power. Here is a brief synergies of GECKO and Gemini. GECKO is kind of a point man to filter and select the transient candidates. After that, Gemini will plays an important role as a confirmation of transient. So we have lots of systems, data reduction pipeline, and the classification of near and forward signal on the image. In that method, we use the AI technique. And after that, we classify the transient type using the color, brightness, and decay rate. After that, Gemini will confirm its transient type. In the view of rapid follow-up observation, it will confirm and characterize the early light curve of the GW counterparts. And in the view of long-term follow observation, it will characterize the late phase light curve of kilonova. And it also, after the kilonova is totally disappeared, we can study the host galaxy properties, for example, the star formation rate, stellar mass, and redshift. So the next gravitational wave observing run is March 2023, and here the expected information of the expected GW events. 50% of binary transfer merger events will have the 30 square degree of localization area, and most of them will emerge within the 170 megaparsec. So as we can see in the result of GW190425, our facility have enough power to cover these events. So we expect more than 2 early kilonova in the first semester in 2023. So here are some take-home messages, and I am Gregory Peg again. I'm the only graduate student who want to looking for the GW counterpart in Korea. So welcome you any comments and blames and questions. Thank you.
Great talk. Questions? On Slack? Okay, I have a question. Can you comment on the advantages and disadvantages of the two strategies, tiling versus
galaxy targeted observation? Great. According to the recent observation, tiling observation really powerful for the fully localized GW event. But we have also the narrow field. We have lots of narrow field of telescopes, so we can leave them. So we have to use all resources. So we adapt both both strategy on every GW event. So yeah.
Some questions on Slack. Oh, great.
Is it on? Yes, okay. When you were doing the rates calculation on the second to last slide,
Great.
the rates,
Great.
the number of kilonovae you might find.
Oh, I see. Yeah.
So I was just wondering, when you calculated that, did you take into account how often all the detectors would be on? So did that does that number take into account that the detectors are off and they cycle through?
You mean duty cycle, right?
Yeah.
Actually, this number is from the paper of gravitational wave detectors team. I mean LIGO. So I think they consider the duty cycle, but I have to check whether it is right or not. So thank you. Thank you for your comments.
Anything on Slack? Okay, let's give another round of applause for Frederick.